And we'll start off with a couple of practical remarks, which I will share my screen. Okay, you should be able to see my PowerPoint. It says week 3 regression. Couple of things, yeah, as the title indicates, today we'll start a new chapter about regression, and we'll talk about what it is and why it is useful in a minute. And we'll spend a little bit of time discussing the data that you all collected. And I have to say, I'm quite glad with how that turned out. So I think about 1/3 of the class, or maybe a bit more than that, sent in their data. So thank you for doing that. If you haven't sent in your data, not a problem. I have another assignment for you during this lecture, so stay tuned for that. And we won't just talk about the data that you collected. We'll also talk about the framework of linear regression, which allows us to make sense of data where you have one variable influencing another. And in fact, today is the start of a rather large chapter, that chapter on linear regression. So on Thursday, we'll have another theory session instead of the practical session that you normally have on Thursday. So this will take place from 9 a.m. to 11:15 via Zoom, and you have the link for that in Eufora. So then we will continue our regression story. And just to sketch a bit what the remaining few weeks look like, or what the next few weeks look like. So we are in week 3 here, as you can see. We have 2 theory lessons and then another theory class 1 week from now. And then you'll have a couple of weeks where you get to practice and play with linear regression. So there will be no less than 3 PC practicals on different aspects of regression, and also 1 session to cover written exercises for regression. And because we're getting close to it, week 5, the week of March the 28th, that is exam week 1 for you, during which you have no class, no theory, and no practical exercises. Okay, that is all the practical announcements that I want to make, except for one. As you've probably seen, I have sent out the grades and the feedback for the practical. I think on the whole, methodologically speaking, the project was good. So I saw a lot of good analyses. I do think there are some general recommendations to be made, sort of what should you include, what should you not include, how should you frame your results. And I will write up a few recommendations, and maybe we'll discuss these in class as well in the next few weeks ahead of project number 2. Okay, so with that, that's all the practical announcements handled, and I will switch to my presentation for today. So if you just bear with me for a second. I will dial in with my iPad. Just a second. Okay, I can see myself. That is already a good start. But I don't want to see myself. I want to see my presentation. Okay. I can see my presentation, so I will assume you can too. Give me a quick shout if you cannot. And we can get going. So as I already mentioned, today we'll be talking about linear regression. Before we dive into what that is and why it is useful, I want to come back to a example for which you furnished the data. So sorry, I had the wrong presentation open there for a second. And that is the following one. So if you remember the email that I sent you, I asked you to measure the width of your right hand across the palm. So if I hold up my hand sort of across like this in the width. And I also asked you to record your height in centimeters and optionally your gender. And I got 26 observations from you, 19 female and 7 male. And then I also added my data, which turned out to be remarkably consistent with yours. So that gives us a fairly decent data set to work with. And we'll dive into the data for right away, but let's talk a little bit about what research questions we are trying to answer or we could answer with data like this, and also what could potentially go wrong. So the research questions basically are, is there an association between a person's height and the width of their palm? Like if they have bigger hands, are they going to be taller? If they have smaller hands, are they going to be smaller? That's a very natural question. And then leading on from that, also, if we have such a relation, if we can quantify that relation, can we use it for prediction? Can we say, well, okay, I have a new person whose hands are 10 centimeters wide. What can I say about the height of that person? Those are natural questions. And then since we're statisticians, we're not just black magicians with data, we do statistics. We also want to know, okay, how confident are we in these results? Is there a very strong relation between the two? Or do we think like, the width of the hand is probably going to influence the height or be related to the height, but there's probably other factors at play. So how strong do we think those results are? And given that we've collected some data and that we have some research questions, now we can also wonder a bit like, who are we trying to talk about? Are we talking about students at GUGC, members of the Korean population, members of the world population? How far do we think our results extend? So in other words, we have maybe obtained a random sample, or we have obtained a sample, but can we argue that this is a random sample? Can you see some sources of bias maybe in how the measurements were obtained? And so on. So I will not go into those questions. They will sort of suggest themselves, and then you can have a think about that, but we'll look right away at the data. So the data that you guys collected is given here on the plot. I have not done any pre-processing. I have not discarded any observations. So this is the raw data as you see it. And right away, there's quite a number of interesting observations that you can make. And some of them are beyond the scope of this class. And some of them are also, they harken back to what we did in the first semester when we thought about hypothesis testing. So for instance, one thing that you can see from the data here is that on average, okay, let me just... Apologies for that. So on average, what we see is the red dots are the females and the blue dots are the males. And we see there is a significant difference in both the width of the palm of the girls in the class and the boys in the class. So these populations are nicely separated. And we also have the same thing for the heights. So you see the bulk of the density is below 170 for the girls, and for boys it pretty much starts at 170 here. Then it goes up to 180, 190. Okay, so you see that on the plot. You can run a hypothesis test to make that more concrete, and you'll get very small p-values, very significant difference. But another thing that we see in this plot is that maybe our intuition is borne out here, in the sense that we see, okay, the larger your hand, typically the taller you will be as a person. And it's not that large hands cause large persons or large persons cause large hands. We can't say in which direction the causation goes, but we can see that there's a clear relation where the bigger your hands, basically the taller you are as a person. And that is what, excuse me, what linear regression is about. So linear regression is a statistical technique where we model the association between two continuous, in most cases, but sometimes also discrete variables, where we want to quantify if variable 1 changes by a certain amount, how much is variable 2 likely to change. So for instance, to make this concrete, if we look at 1 centimeter difference in the width of a person's palms, then how much taller do we think they are going to be on average? And if we look at, roughly speaking, I think the vertical distance here is about 10 centimeters. So this relation allows us to say 2 people that differ in hand size by 1 centimeter will on average differ in height by 10 centimeters. Not everything can be captured in such a nice, clear, linear relationship where you have a line giving you the trend in the data. We will see that in this course. But in many cases, or at least in a number of significant cases, this is indeed what happens. Okay, so now the next thing is I've drawn that line sort of by looking at the data. We can do better. We can ask R for that line, and we'll see how we do that in the bulk of the course. But here you already see the results. So we've asked R, give me the line that best predicts the height based on palm width, or that best associates those two variables. And R has come up with the dense line that you have here in the middle. So this is the line of best fit. And that line has this prescription. So you see the intercept is 87.45 centimeters and the slope is 9.91. And we'll interpret the slope as if the width of your hand is different by 1 centimeter, how much different is your height on average. And the intercept is a little bit less important as a parameter on its own. The intercept tells me for a person whose hands have 0 width, how tall is that person? On average, 87.45 centimeters. That is, of course, a nonsensical conclusion based on the fact that I'm extrapolating beyond the validity of my model. But that's one possible interpretation of the intercept. And then we also have these shaded lines on either side. And the shaded lines give me an upper and a lower bound of a 95% confidence interval on that line. So this is 95% upper, and this is 95% lower. And what kind of confidence interval is it? Well, it's a confidence interval on the line itself. So it's R telling us, or statistics telling us, how certain am I, or how confident am I about the line that I predict? And here, narrow, as always with confidence intervals, means better, means more accurate estimates. So here we see actually that the band is quite narrow. So we can be quite confident about our line. We will go into the output of R a little bit more in detail, but a couple of things that you can derive or that you can already see, which are going to be significant here, is we see the coefficients here, 87.45 and 9.911, the ones that I had on the plot. And we also have some indication about how confident we are about these values. So we have p-values here. P-values that tell us something about, do we think that these coefficients are significant or not? Do we think these coefficients are different from 0 or not? So let me maybe write that down. P-values for a test if the parameter is 0. Why 0? Why are we interested in doing a test if it's 0? Typically because for the slope, at least, 0 means that variable 1 has no effect on variable 2. So if the coefficient for palm width, let's say if this was very close to 0, then we would say probably palm width does not associate well with height. And then a couple more things that we will see in not this class, but the next few ones, is this R squared value, which tells us about how well the linear regression explains the variance that I have in the data, or how well it explains the data. So you can imagine a good fit or not so good fit. R will happily draw a straight line through either data set, but as a diagnostic, you have that R squared value that tells you basically the higher it is, the closer to 1 it is, the more the line explains what you see in the data, and the lower it is, the less informative the line is. So I have a question in the chat box about whether the line of best fit is different from a trend line. So it depends a bit what you mean by trend line, how you model your data. But in my vocabulary, this line of best fit is an example of a trend line where you observe what on average the data looks like, what the trend in the data is. And it is an example because linear regression, or at least the simple linear regression that we will cover, works with straight lines. Okay, I will be very brief about this plot. This is also made with R, and we will dissect this plot in this course. But linear regression, as with every statistical technique, comes with a number of assumptions that need to be guaranteed before you can confidently draw conclusions from your model. So again, R is a piece of software, or the statistical technique. It's a calculation that you do. So you can do it no matter how poorly your data fits a linear model, but the results will not make sense. And in order to have confidence in your results, and in order to know whether or not the underlying assumptions are valid, there's 4 assumptions, and we will use these plots to corroborate the assumptions. And the only reason why I'm showing them now without explaining them is because I want to draw your attention that actually this data, for being real life data, is quite linear and quite well fitted by a linear model. So I was actually quite surprised when I saw that. I thought I would have to do some transformations and some adjustments and maybe fit a higher order model, but no, straight line fits our height and width data quite well. And then the last thing that I want to show you here is now that we have our model again with our trend line, y is, I forgot what it was, I think 87.9.9 times the height, or say times x. So we have our trend line now, or a line of best fits, or linear regression line. Now we can also ask the model, if I have a new person, let's say with a palm width of 10 centimeters, how confident, or what can I say about the expected height that person has? And here what I can do is I can plug my data into my linear regression line. So if x is 10, then I have that y is 87 plus 99. So 9.9 times 10, and that is 186 centimeters. So someone with palm size 10 centimeters will have, on average, a height of 187 centimeters. And we are talking about statistics, we are talking about uncertainty. So that person is not going to have height exactly 186 centimeters, right? There's always going to be some source of error that makes it a little bit more or a little bit less. Nevertheless, if the assumptions of our linear model are satisfied, then we can ask the model about how sure it is about these kind of predictions, or what the uncertainty is. And that is the broad band that you see in the plot, the dashed lines. So these are the upper and the lower bound of a prediction interval. And what that means is that we are 95% confident that a person who has height, who has palm width 10 centimeters will have height in this interval. So if I extrapolate it a bit, we are 95% certain that their height will be in this interval. Let me just scribble over it. So from about, let's say this is probably 173, and then 14 extra, so 197,201. So the numbers, I'm just eyeballing them, but we are 95% confident that their height will be between 173 centimeters and 201 centimeters, 2 meters 1 centimeter. And you might say, well, that looks a bit imprecise, but yeah, that is what the data tells us. So if you haven't already submitted your data, here's your next assignment. So you have the expression for the trend line here. Measure the width of your palm of your hand. Check with your data and try to eyeball, like, is this within the prediction interval that I think that I can see from this figure, or do I have some measurements that are completely off? So I will not ask you to send that data. The experiment is done at this point, but just as a corroboration, you can plug your data into this model and really see if it makes sense. Okay, so that was the introduction, and I thank you for sending the data. Again, I think this really makes a difference. And what we will do now is we'll dig a bit deeper into the assumptions behind the linear model and how to build up the model ourselves from scratch. Okay, so you should have also this slide deck on Eufora. And yeah, maybe just a quick word about the slide decks that I post. I try to make them available before the start of the class so that you can write on them as well. But sometimes, like today, I have to admit, I work on the slide decks until very shortly before the actual class. So I do ask for your understanding if they don't appear the day before. I try to post them early on, but sometimes that doesn't happen for a variety of reasons. Nevertheless, yeah, we'll always make the slide decks available afterwards with the annotations. So for the rest of today, let's talk about what is labeled here as a simple linear regression. And you can put the simple here in quotation marks, because as you will see, this is not a simple or a straightforward technique. This is a very powerful technique, but it just means that we will have only one predictor. So we will try to predict y, or we will model y as a function of x. So for instance, height as a function of the palm width, but we only have one thing on the x-axis. And then in the next lecture, we will talk about multiple linear regression. Where now you have several independent variables that can affect the outcome. And for instance, what we can say is, well, okay, my height depends on my palm width. I've already seen it, but maybe it also depends on my gender, G. And maybe there's a few other factors that also play a role. Maybe the country that I come from has a role, and so on. So in this case, we have multiple independent variables that conspire to give us an outcome. So throughout this course, we will, or at least for today, we will use one specific example of modeling coastlines in North American lakes. And what we will look at in particular is the following. So we have a study, and this study is also described in your course notes in chapter 7. So for more details and for a closer look at the models, I would recommend you read up on that as well. What we do in this study is we are interested in the riparian areas of lakes in North America. And what are these riparian or riparian areas? Well, they're the areas close to the water where trees grow right on the shore. So you have a lake, somewhere, and then around that lake on the shores you have forest, and that is what we call the riparian area. the trees on the shore of the lake. And what we want to know now is something that climatologists are interested in. So we know that, hey, these trees that grow on the edge of the lake, they will decay, branches will fall off and so on, and they'll leave what is known as coarse woody debris. So basically pieces of wood in the lake. And then these pieces of wood, they change the constitution of the lake. They provide a habitat for animals and so on. And what we want to know now is there a relation between the density of trees along the lake and the area of these, where these coarse wooden debris can be found? And intuitively, you probably say, well, yeah, there's probably going to be such a relation, because if there's more trees along the edge of the lake, more trees means more woody debris that fall into the lake, hence larger areas where you can find wooden debris. So it intuitively makes sense that there is such a relationship, that there is a positive correlation, but now let's see if the data bears that out. So a bit of terminology. So first of all, what we will model is the area where these coarse wooden debris can be found in square kilometers. And this is the thing that we are interested in, the outcome. So we want to see how that changes based on other variables, but this is what we call the outcome, or the response, or the dependent variable. We will use those terms interchangeably. And then the other thing that we know about is the tree density along the lake, and that is our independent variable, or our explanatory variable, or our predictor. And what we basically want to see is if the tree density changes, or if we have different lakes with different tree densities, what is the difference in the coarse wooden debris basal area? With the risk of maybe going a bit off topic, one thing that I want to caution against is trying to make a causal connection. So don't say increase in tree density causes increase in coarse wooden debris area, because we cannot, with this kind of studies, infer whether one thing causes another or not. The only thing that we can say is these two variables are related more or less. Think a bit about if you have a linear regression where your palm width is associated with your height. It would be wrong to say bigger palms cause bigger people, and it would equally be wrong to say bigger people cause bigger hands a priori. But what we can say is that the two variables are related. So here we have the data from the 16 lakes. So we have a scatter plot. Making a scatter plot is always a good idea when you start off with regression, because then you can hopefully already see that there's yes or no a linear relation, and B, if your data doesn't quite fit the linear model, it might also tell you what precisely goes wrong. So what we have here is the data as already mentioned. The straight line is the line of best fit that R gives us, the regression line. And then the dashed line is this Loess estimator, which we will not go into, but it's an advanced statistical modeling technique to basically model with a lot of parameters what the optimal, in a certain sense, the optimal trend is through the data. And why do we plot that Loess estimator here? Because if we compare it to the line of best fit, the linear regression line, we see it's actually quite close. So even the fancy statistical estimator that uses all sorts of nonlinear modeling under the hood says, hey, the trend in this data is pretty linear. So let's go a bit into the assumptions and build up a linear model from this point on. So what we typically have in any kind of model, not just in a linear model, but in any kind of model, is that we have two variables, x and y, that we want to correlate. And we know that correlation or that association is going to introduce some relation between the two. But since we are working with real world data, that relation is never going to be exact. There's always going to be some noise that we have to take into account, noise that can come from the measurements in your observations, or that can come from the fact that there are hidden factors that you don't quite see in your model, and so on. If you think a bit about what you did when you measured your hands, you probably noticed the measurement of your palm width changes depending on how you put your measuring rule. Like if you put it really flat, maybe your hand stretches a bit and you add a few millimeters. If it's not entirely at right angles to your hand, you also add some noise, and so on. So we also have to keep in mind that our observations are part signal and part noise. And we can describe that mathematically by saying, well, our outcome, y, is going to be a function of the dependent variable or the predictor x. And what that function is, that is determined by your model. But then we also have to add some noise here, epsilon I. And without really losing generality, what we will do is we will take this noise to have zero mean. So if we take the average of the noise, we will assume that it is zero for all the subjects that have the same xi. So that's what we have here in this relation. And again, you can sort of see that makes sense. If you take a lot of students and you have them all measure the size of the palm of their hand, some will over measure, some will under measure, but on average, the errors will cancel out in the long run if you have many students. So we say that the average of the noise is zero. And so if we make that assumption, then we can also say that the function f here is going to be the expected outcome for subjects with a given value of x. So why is that the case? Well, keep in mind, if we take the expected value of y for a given x, then that is, according to our model, fxy plus epsilon yi, given that x is some value x. And because of linearity, I can write this as the expected value of f of x plus the expected value of the noise. And as I have above that, the expected value of the noise is precisely zero. And what is the expectation of f of x, given that x is little x, that is set to a particular value x? Well, there's no uncertainty in that f. This is not a random variable. So this is just f of x. So what we have here, the f of x, that's going to give me basically the expected or the average outcome for a given value of the predictor. And now, how do we get to linear regression? Well, for linear regression, we assume that f of x is a linear function of x. So we assume that it is given by an intercept alpha plus a slope beta times x. So the simplest function that we can imagine. And it turns out that this is, of course, an assumption, so it can be wrong, but in a lot of realistic data sets, this is a valid model, this is quite a powerful model. So again, refer back to the palm width versus height, where you could clearly see that these two things were linearly related, and I give you a good fit. So what can we do with linear regression? Well, there's two things that are important. One is prediction. So if we have a value for the predictor, so for instance, if we know your palm width, then we can predict y, we can predict the outcome, for instance, the height in our example, based on x. And how do we do that? Well, we use our relation or mathematical relation that says the expected height given your palm width is a linear function alpha plus beta x, and then you just plug in what x is. So I already did that in the previous slide deck. If we said, hey, let's take a person whose palm width is 10 centimeters, what is their expected height? Well, it was 87 plus 9.9 times 10, or 186 centimeters. So we expect their height to be 186 centimeters. So here you have to again keep in mind that the predictions that you get out are averages, and they are subject to uncertainty, and we'll describe that uncertainty later on. And the second thing that you can do with linear regression is association. If you have one variable x and another variable y, let's say a measurement, then you can describe how strong is the relation between the two. If the tree density increases, by how much do I expect the CWD basal area to increase? If the palm width increases, by how much do I expect the height of the person to increase? And this is where the slope of the regression line comes in. So this beta is the slope. And what we can do to tease that out is we can ask, well, on average, what is the difference in the outcome, y, for two people or for two measurements that differ by delta in the predictor? So I ask for the expected value of y, given that x is some value x plus a little bit, plus delta, minus the expected value of the outcome, given that x is just x. So the difference here is in what my predictor is. So I compare people with palm width, let's say 9.5 centimeter, with people with palm width 9 centimeter. And I ask, on average, what is the difference in height between the two? So I again use my linear relation that I have up here, and I write the first term. I can write the first term as alpha plus beta times x plus delta. And the second term, so this is the first term, and then the second term is the second expectation here, and that is just alpha plus beta x. So I subtract that from what I had previously. And you see quite nicely the intercepts cancel out. The beta x's also cancel out, and I'm left with beta delta here as the result. And how should I interpret that? Well, in words, the difference in average outcome between two subjects that differ by delta units in the predictor is beta times delta. So in particular, if delta is 1, so if the subjects differ by 1 unit, two people with palm width 9 centimeters and palm width 10 centimeters, they will differ beta units in the outcome. So for the height example, again, the slope beta was 9.9 centimeters. And we said early on, if your hand size is different by 1 centimeter, we expect you to be different in height by 9.9 centimeters. So the slope tells you precisely that. And this is why the slope is an important parameter, because it tells us how strong the association is. Higher slope means stronger association. Lower slope, close to zero, means less of a correlation. So now, how do we find these coefficients alpha and beta? So they are parameters of our model, and we need to find them, or we need to fix them to an appropriate value before we can actually describe something. So we will go into the derivation of this a bit later in this course when we talk about optimization. So I will put this up for then. But basically what we will do is we'll work from the idea that the regression line, the least squares line, is the line that best fits the data. And how do we interpret this best fit? Well, we're going to look at the residual. So the residual is basically, we typically call it E. And the residual E is the difference between the actual outcome for an observation, so yi, minus what the model thinks it is, alpha plus beta xi. So that is the residual, is basically how much difference is there between what the model thinks it is and the actual outcome. So we can write this as, this is the actual outcome and this is the predicted outcome. And so that gives us the residual for one observation, observation I. And now to take into account all observations, what we do is we take the residuals, we square them to make them all positive, and we add them together. And that's going to give me a complex function or a complicated function of alpha and beta. But that is the thing that I want to know about. And so I see a question. Isn't the actual outcome yi? Yes. Yeah, so maybe just to answer the question, or at least put it a bit more sharply. So yes, what I have in my model is I have data points x, y, I, y, so n of them, y going from 1 to n. And so yi is the actual outcome in the data points, and alpha plus beta xi, that is what the line predicts, what the average is for that class. I hope that makes sense, but ping me if it doesn't. So that gives me my residual. And now what I have to do is, this gives me a function which I'll call j, or actually let me use the terminology that we'll use later, L alpha beta. So yi and xi are givens, they are the data points in my data set. Alpha and beta are parameters that I have to determine. So that's why I write L, the function I want to optimize, as a function of alpha and beta. So now what I have to do is basically find alpha and beta that minimize this sum of squares. So I have to wiggle alpha and beta about until L, the objective function, becomes minimal. And how can I do that? Well, I can of course do this in a very handy way by trying values, trying things out, and seeing what will give you a minimum, which parameters are the best. But I can also use calculus. So I can say, well, if I have a minimum, then the partial derivatives of L with respect to alpha and with respect to beta have to be equal to 0. So this is a necessary but actually not sufficient condition in general for having a minimum, but in this case, since we have a function of a specific form, it is actually sufficient. So under the hood, when you ask R for a linear model, what it basically does is it computes these derivatives in a certain way, and then uses those to find alpha and beta. So we will not go into the exact calculation, even though we can until a bit later. But I just want to give you the result. So the slope parameter beta, if you do this calculation, you'll get that the slope is given by the correlation between x and y times the sample standard deviation in y divided by the sample standard deviation in x, or the standard deviation in x. So the correlation and then the standard deviation in y and divided by the standard deviation in x. And intuitively, that makes sense. So remember the correlation between two variables, we saw that way back at the beginning, measures how strong the association is between the two variables on a scale of -1 to 1. And you can see if there's a stronger association between the two variables, you're also going to have a steeper line in a steeper linear regression line. If you have more variability in y, that also will increase the expected value of your slope. And then conversely, if you have more variability in x, that will decrease the estimate for your slope. So once you have beta, then you can also find the intercept. And the intercept actually depends on the value of beta. So here you take the mean of your y, of your outcomes, and you subtract from that the value that you found for beta hat here, times the mean of your x's, of your predictors. And that will give you a value for the slope. And I see a question in the chat box. What does the hat symbol mean? It's a very good question. It's something that sometimes we do gloss over a bit. So basically to make it maybe into a bit of a long story, so these alpha and beta, they are basically random variables because they depend on what data I have in my sample. So if I have a different data set from the same population, I'm going to get different alpha and beta. And then alpha hat and beta hat, they refer to estimates that I make of those parameters. So the hat notation means I have an estimate of the population parameters alpha or beta. So to put it maybe in an intuitive, slightly rough way, alpha hat and beta hat are the recipes that we use to compute these parameters. So they're basically recipes that you put in your data and you get back a number. That's what alpha hat and beta hat give you. And here I have basically a plot of what these residuals look like together with a line of best fit. So let's say we have a data point here in our data set with xi around 1800 and yi around 1/3. Sorry, that's not correct. Let me erase that. Yi around 180. Then the length of this segment here from the regression line to the data point itself, that line, the length of that segment is the residual EY. Why is that? Well, what we have here, this point where the segment hits the regression line, this point has Y coordinates alpha plus beta times xy, which in this case is going to be about, I think I said 130, roughly speaking. So what I see for the residual is that the residual is, in this case, approximately 180. The actual value, let me write it in color, 180 minus the predicted value if you just look at the regression line, so 130. So that is about 50. And you see here that residual is 50. So in the objective function, that's going to contribute 50 squared or 2,500. And then the goal of finding that line of linear regression is to minimize these residuals. So you square them, you add them all together, and then you change the line, you move it up and down, and you change its slope so that the sum squared of the residuals becomes minimal. We can compute things by hand, as the previous slide showed, and that's how people did linear regression for a very long time. But of course, we can also use R, and that is the recommended way, because at this point, except for a few simple examples where you can compute the correlation and the standard deviations exactly, it gets quite tedious if you have to do that for 10, 20, 100 observations. So that's why we have a lot of practical sessions, because yeah, from this point on, we're going to be working with data sets, and we need to save ourselves a lot of computations and basically rely on R to do that for us, so that we can talk about the conclusions instead. So the way that you run a linear regression in R is quite straightforward. You use the LM command for linear model, and then you give it an argument that is a formula. And formulas are always of the form some outcome, Y, and then tilde, some predictor or some independent variable X. And then R will basically regress the outcome on the predictor. So in this case, we're interested in the effect of the riparian density, the number of trees per square kilometer along the lake. And the outcome is the basal area, of course, within debris, which in this case is the variable cwd.base A. That will give you a model object, and then you can query that model object in R to find the information that you're interested in. So oftentimes we will want to know the coefficients of the linear model. So if you ask for, if you use the summary command with that model as an argument, then you will get actually more outputs than is shown here on the slide. But amongst that, you'll have a small section coefficients. And here again, you can see in the coefficients, you have the point estimates. This is our alpha hat, and this is our beta hat. And this allows us to conclude that for that particular example, the expected basal area given the number of trees is minus 77.10 plus 0.12 times x, the value of the number of trees that we have at that location. The other columns we'll go into later, but let's see a bit how far we can take this model. So on the top, I have again the linear model as R gave it to me. And let's talk a bit about the interpretation of the coefficients again. So I've already mentioned in the beginning when we did a theoretical calculation that the slope beta, or beta hat to be precise, is the difference in outcome, or the expected difference in outcome, given that the subjects are 1 unit in difference. So what that means is, if I have 2 lakes with 1 tree per kilometer more, then I expect there to be 0.12 square meters larger coastal areas between the two. Talking about 0.12 is a little bit cumbersome. So what I can do is I can say, well, instead of talking about 1 unit in difference, I'm going to talk about 10 units in difference. So then what I can conclude is that if I have 2 lakes that are completely the same, except for the fact that they have that one has 10 more trees per kilometer than the other, then what the difference in expected basal area is beta times the number of units that are different. So 0.12 times 10, or 1.2. So that's how I get the 1.2 here. So 1 unit difference gives me an expected difference in the outcome of 0.12. 10 units gives me 1.2 expected difference. Now, I can also ask the model to generate new values. I can do prediction. I can ask, well, what happens, or what do you think the expected basal area is if I have 1,600 trees per kilometer of shoreline? Well, what I do is I plug in 1,600 for X, and I calculate, I get an expected area of 108 square meters. But you have to be a bit careful if you push this model beyond the limits, or beyond the scope of the data that it was calibrated on. Because, for instance, if we ask for the expected area for 500 trees per kilometer, then what we get out is a negative value, which is obviously not physical. Likewise, if we ask, well, what is the expected number, what is the expected basal area when there's no trees, when X is 0, then we get minus 77, which is again negative, doesn't make sense. So now for the last part, and then we'll take a quick break. We'll talk a bit more about the assumptions that undergird linear regression, because we are a bit lucky in the sense that running a linear regression isn't difficult. You've seen the R command, it's literally one command. But before we can actually do that, we have to make sure that the thing that we are trying to model is in fact somewhat linear. So the first thing is we want to fit a linear regression to data sets that look linear, or that are modeled by a linear process. So that may sound like a tautology, but it is something that you have to check. If you have data that is not linear and you try to fit a straight line and then draw some conclusions from it, you're going to run into trouble. So what you can do to verify the linearity assumption is what we already had in the previous slides. You can look at a scatter plot. It's always a good idea, except that it may not always give you a lot of information. If you have a lot of data, it might be informative. But here, for instance, if we look at the data, we see, yeah, this data looks linear, but we may not be entirely convinced. So what we can do instead is we can go look at a regression, at a residual plot, excuse me. And this is going to give us a bit more powerful insight into whether the relation is linear or not. And moreover, this is also going to work well in the case of multiple predictors. So you'll see in the next class, if we have multiple predictors, then scatter plots are going to be useful, but they may hide some of the complications of the data that we have. So in that case, looking at the residuals is going to be more appropriate. So as a reminder, what are the residuals? Well, the residuals are basically what you get if you compare the actual outcome again with the predicted outcome, and you take the difference. And what we expect is if our linear model is correct, then if we plot the residuals as a function of the x variables, then we expect to see no pattern. So we expect on average there to be like just uniform distribution of the residuals. We can make this prediction, this residual plot ourselves, or we can ask R for it. And if we do that, so if we make our model as we have here, and then we just do plot model, then we will get a grand total of 4 plots, where in this case, we are interested in the first one right here. And what we see is what we have on the x-axis is the fitted values, actually the alpha plus beta times x's. And on the y-axis, we have the residuals. And there's not a lot of data, but you can see to a certain extent, there is no obvious pattern here in the data. So we also have the red line, which R adds for us, which is, again, one of those trend lines. And you can see, you want that trend line to be flat. You want R to say, like, I discover no pattern in that data. Here we see it's somewhat bumpy, flat but bumpy. We will see why that is in the next hour. But suffice to say, for now, this looks reasonably linear to us. So then 2 more assumptions that we have to take into account. When we want to draw conclusions about our linear regression model, we also need to know a little bit what is in the noise that our model has. So remember, our models are always signal plus some noise, and it's the noise that tells us a little bit how certain can we be about a certain prediction. We know that with the height measurements, we know we don't get an exact measurement back. There's always some noise. And depending on the assumptions that go into our model, that can change or affect how strong our conclusions are. And so there are 2 assumptions here to be made separately. And one has, the first one, let's talk about the first one, has a quite forbidding name, homoskedasticity, which is a term that you'll see occur quite a bit in statistical treatments. And that is basically saying that for a given value of the predictor, the outcome has to have constant variance. So this constant variance part is what homoskedasticity refers to. And we can actually estimate what that variance should look like from the data. And how can we do that? Well, we can again go look at the residuals. And that kind of makes sense because the residuals tell you how far the observations are from the linear regression line. So if the observations are on average far from the regression line, then we think there's probably going to be a lot of variance. And if they are close together to the regression line, then there is likely to be not a lot of variance. And we can actually, so R will do this for us, but we can calculate this exactly. We can estimate this from our data by taking the residuals squared, summing them together, and dividing by the number of observations -2. And that gives us the residual mean squared error. So that's one condition, and we'll talk about how to check that in a minute. And the other one is normality. So for normality, what we want is actually something that's a bit stronger. For a given value of the predictor, we want the outcome to be normally distributed with variance sigma squared that came from the homoscedasticity. So let's unpack these a little bit more in detail and see what that means for our data. So here I have, and I see, let me just make a quick stop. Question about the previous slide. So yes, here, let me recap the question. So the question is, for fixed x, does that mean the same x and y? So here the way to read this sentence is, for fixed x, y is normally distributed. So you fix x, you take all the people with palm with 7.5 centimeters, and you look at their heights. So you let y vary. You fix x, and then you look at all the y values in your data set that correspond to that x. And I'll give an example on the next slide, or slides. So first, let's talk about this homoscedasticity. What does that look like on a scatter plot? So again, that means that for fixed x, and let me also make the caveat here. So if you take a small slice of x and you look at all the observations in that small slice, then the variability in the outcomes needs to be approximately needs to be constant. And we see on the, let me actually erase this because this is a bit clumsy. You can see here all of the observations are in this band of about 1 unit wide. So for each value of x, if I take x0, then the observations that correspond here with that are going to have variance about, or standard deviation about this. And likewise, if I take x is equal to 2, then the standard deviation or the variance is going to be about 1. So I see this band has constant width along the trend line. So that's what homoscedasticity or constant variance means. And by contrast, on the right here, we have heteroscedasticity, which means not constant variance. And here you can see the observations are tightly clustered in the beginning, but then they fan out like this. So here, the variance is quite narrow, and here the variance is quite wide. So it's again quite difficult to see homoscedasticity on a scatter plot if you don't have a lot of data. So we will have to make a recourse, or we'll have to do something a bit more involved. What we can do is we can plot the squared residuals and use those to basically figure out what the variance looks like. So again, remember, if my residuals are big, that's an indication that the variance is going to be big. If they're small, that's an indication that the variance is small. If they change as a function of x, that's going to be an indication that homoscedasticity is violated. And so let me see. Yeah. Okay. So we can do that and come up with the following plot. As a matter of fact, so here I have my my x values on the x-axis. So my riparian densities on the x-axis. And then on the y-axis, I have the squares of my residuals. And so the dots are the squares of my residuals. That's what I can plot. And then the straight line is, again, a trend line. And I can see, so what I want to see for homoscedasticity is no pattern in the data. So no trends in the squared residuals. And I see that that's maybe not entirely true, because I see my residuals go up on the whole up until 1400, let's say, and then they are flat. So I do see a little bit of a pattern, which makes me think like, hey, maybe this assumption of constant variance isn't totally justified. So now R will also give us that plot. We don't have to make it by hand, but we can if we choose to. And that plot is the plot here that you have on the lower left. So this is the second plot that we've considered. So the first one was this one for the linearity assumption. And now we look at the second plot here. This is not entirely the same plot as what I had on the previous slide, because here we have the square root of the residuals on the y-axis instead of the square of the residuals. But the message stays the same. So here you want to see for homoscedasticity, you want to see no pattern in residuals. And here we do see a pattern. We see this increase as our fitted value increases. So this is food or pause for, should give us some pause for thought. And then just before we take a break, one more thing about the, so let's come back to the other assumption, the normality of the observations that we want to see. So here, what we want to see is basically that the if we fix X, if we take all the people with a given palm width, we want the heights, or we want the outcomes to be normally distributed. And we know a bit about, well, what are the parameters of the normal distribution? Well, we know the mean. That's going to be the value at the linear regression line, A plus B times X. And we know the variance. That's what we can estimate from the data with that residual mean squared error, or what we can observe from our scatter plot. So we know the parameters, just have to see, well, does the distribution actually look normal? And here, what you can use is, you can use, again, the residuals, but now by making a QQ plot of the residuals. And why is that the case? This is the last thing, and then we'll take a break, I promise. Let's again look at some synthetic data and see how that plays out. So here I have data that is normally distributed. I have data on the left-hand side, X versus Y, synthetically generated data with R. And I've set it up in such a way that for each fixed value of X, the corresponding Y values are normally distributed. And you can see that. So in particular, we have homoscedasticity. Everything is in a nice narrow band like this. And now what we can do on the right-hand side here is we can chop the range of the X-axis into small pieces like this. Let's say all the observations from 3.5 to 4.5. And we can take these observations and make a box plot of them. So we take the green observation and we put them in a box plot, and that gives us this box plot. And we can do the same thing. We can bin the other data. So we can, for instance, take the observations around 8, let's say from 7.5 to 8.5, and like this. Take all these observations that are more or less 8, and then put them in a box plot here. And we can do that for every sort of, so we can divide the x-axis into a number of pieces and then make a box plot for the data in every piece. That's more or less what it means to fix x and to look at the outcome. And if we do that, then we get this range of box plots. And we see that, yes, these look like box plots that come from normal distributions. So the median is nicely in the middle, more or less. The whiskers don't indicate any skew. It's nicely symmetric. And we only have a few outliers consistent, again, with a normal distribution. If you say at this point, I don't want to go making box plots based on this rather arbitrary binning, and besides, I can't look at a box plot and say whether it's a normal distribution or not, then I give you 100, I agree 100% with you. I also cannot see that this is a distribution for which the normal, or a model for which the normal distribution holds. But what I can tell you is that we will not look at this to validate the assumption. We will look at a QQ plot. But this plot is just to show you, hey, this is what it would look like if you made the box plots. So let's compare it with a distribution or a model where the normal assumption is not valid. So here what I see is that, yeah, homoscedasticity is not going to be valid because, again, I see the observations fanning out and the variance becomes bigger as x increases. And likewise, what I see is that these distributions on the right-hand side made in exactly the same way, that they're not normal distributions by a long shot. We see they're very right skewed. So especially here on the right, we have severe right skew in our distribution. So not normally distributed. Okay, so this gives you some insight into what the data looks like, but now how do you check the assumption? Well, what you do is you make a QQ plot of the residuals. And here the fact that it's the residuals is important because the residuals are what encodes the variance in y of x. And if you take again the data that I had that was normal by construction, the one where the box plots looked like what it is on the left. And now if you make a QQ plot of that data, then you see that data is nicely distributed along a straight line. So very nice fit with normality. It's very important to take a QQ plot of the residuals. If you take a QQ plot of and just to contrast it, if we take our not normal distribution for y given x, and we make that residual QQ plot, then we see deviation from normality here and here. So the assumption is not satisfied. And then just the last thing here is do not use the QQ plot of y itself. Always use the QQ plot of the residuals. So the residuals, because making a QQ plot of the outcomes is a much stronger assumption, and you will see that assumption is not always valid. So do not make a QQ plot of the outcomes. Okay, so with that, I've gone over time a little bit for this first hour. We will stop here and take a break until about 11:40, and then we will continue with the rest of today's lecture. So thanks for your attention so far, and see you at 11:40. All right, everybody, we're back. Let's wrap up our assumptions and then see what else we can do with regression. So the last thing that I mentioned before the break is that to check the normality assumption, that entails making a QQ plot of the residuals. And luckily, R also does that for us. That is the third plot that we see here in the output. That is the one on the top right. So if we interpret that for our data set at hand here, we see that, yeah, well, maybe the normality assumption isn't quite that well justified. I see I saw a question just coming in about group feedback for the first assignment. I will send you for that directly to the TA. So I'll make an announcement via Eufora because since the TAs graded the assignment, they will be able to provide feedback if you need it. So I will tell you which TA to attend, and then you can make an appointment from there. Okay, so that gives us our assumptions. Now let's put those aside for a second and let's talk about what we can do with linear regression. So first of all, what we are interested in is the slope most of the times, so our parameter beta. And what we want to do now is we want to draw conclusions, statistical conclusions about that slope. And why do we want to do that? Well, look at the following two data sets. If we have a data set that looks like this, then the trend line, the linear regression line, is probably going to be like this. Beta is going to be very small, approximately 0. And here we would like to say that there is no association between X and Y. And why is there no association? Because you see X varies here, but Y doesn't vary a lot in response. The only variation in Y that you see is due to noise. Whereas in contrast, if we have a data set that looks like this, then we do have a strong association between the two. Beta is going to be larger than 0. And here, oops, we have a strong association between the two variables. And in statistical decision making, we're interested in distinguishing the first case from the second, because the first one says there's no effect, there's no relation between the two, and the second one says there is a significant or strong association. And so for that, in order to distinguish between the two, we need to look at beta and at its value. And so what we have is that beta itself is, as I mentioned, is a random variable. So you take a different sample, you get a different beta value back. And what we've done, and so a good follow-up question from someone in the audience saying, what if beta is negative? That's fine too. That means there's an equally strong relationship, but a negative association. So X becomes larger means Y becomes smaller, but that's fine. Well, depending on what we're interested in. But the dichotomy is between, we want to check, is there an association versus is there no association? And then whether it's a positive association or a negative association, that's something that we can see from the sign of beta. But mostly what we're interested in here is beta equal to 0 versus beta not equal to 0. So, okay. with that, so we have already established our formula for what we think beta is based on that minimization procedure. And here, what we also know is that beta hat is an unbiased estimator. So what that means is that over the long run, on average, beta will be approximately the true population parameter, or will tend to the true population parameter. We have to keep in mind it's not it's an estimate of what our true population parameter looks like. It's an estimate that has error. And fortunately, there's a formula that we can derive for the error on beta hat. And it's given down below here. You don't have to use it because, or you don't have to memorize it, because we will mostly use it from within R. But it is basically given by the square root of the mean squared error, which is 1 over the number of observations times the sum of the squares of the, again, these are the residuals. This yi here is a plus b times xi. And so we take the sum squared of the residuals, and then we divide by the sum of the x's minus the mean of the x coordinates. So this is again the mean. And what that means is that, so that gives us an estimate for the standard error on beta. And that is useful because now we can say, well, okay, how, well, we can use it to basically build a confidence interval for beta. And that is useful because let's say that beta is very small, but not equal to 0, then we want to know, like, is that significantly different from 0 or not? Or we want to know, like, how confident are we about our estimate of beta? Well, the estimator said it's 0.5, but what is the error on that estimate? If the error is 0.1, then we can be quite certain or can be quite confident that it is significantly different from 1. If the estimate is 0.5, but the standard error is also 0.5, then we basically know nothing, because it could be 1, it could be minus 0.5, all of those values are likely. Yes, and I made a small mistake here. So y hat, it is y hat, that is a plus b xi. So what else do we see from that formula? And so if the standard error scales with the mean squared error, so if the mean squared error is larger, the standard error is also going to be larger. That's to be expected. If our residuals are wider, then we have less, we will be less confident about the slope of our line. But what we also see is that in the denominator here, we have that term xi minus x bar, mean of x. So those individual terms, what they basically mean is, or what they refer to is how far the x's are away from the mean in the x value. So what that means is that if the observations are bunched together on the x-axis, xi will be approximately x bar, x mean, and those terms in the denominator will be small. If those terms are small, since they're in the denominator, the standard error will be large, because a small number in the denominator means a large number overall. Conversely, if xi, so let me maybe write that down. So if xi minus x bar is small, that means the observations are bunched together. So small spread on observations, and therefore the standard error will increase. And conversely, if these deviations are large, then that means a large spread on the observations, and that will cause the standard error to go down. And we can see that in action on the following figure. So here on the left, we have that xi minus x bar is large. So we have a large spread on our observations. And that gives us, or that will give us a linear model that is well fitted to the data, where the uncertainty on the slope, the standard error for beta, is small. And conversely, you can see here on the right that xi minus x bar is small. And so that means small spread. The observations are very bunched together. And you can see it would be quite difficult, even by hand, to draw a fitting line through that. Like we have the line that R thinks is the right one. But if I told you, well, R thinks it's this line, or R thinks it's that line, you would probably not be able to tell based on the figure that those lines are more or less likely. So here we have a large standard deviation or a large standard error on the slope, corresponding to the fact that we are quite uncertain about what the line of best fit looks like. On the left, on the other hand, it's pretty clear that the given line is the line of best fit. If I told you the line of best fit is this, you would immediately disagree. You would say that cannot make sense. So here it's hard to pinpoint. On the right, it's hard to pinpoint down the line of best fit. So now we have our standard error. We can build a confidence interval for the slope. And in order to do that, we need just a little bit more. We need to know how the slope as a statistical parameter is distributed. And because it's basically built out of squares that we add together, it will be given by a t-distribution with n-2 degrees of freedom. And I need to be a bit more careful. So it's not the slope itself that is t-distributed. It's the estimate that you get for the slope minus the population parameter and then normalized by the standard error that is t-distributed. So fortunately for us, so we can, and I think there is an exercise where you have to use these or where you have to use this in some shape or form. But R also gives us the required outputs in order to do calculations with it. So let's look at the coefficients here that we get from R. So we've already talked about the fact that we get the point estimates down below here. But now what we see in the next column is we get the standard errors. And the standard error that we will be most interested in is the one on the slope. We don't really care about the standard error for the intercept because we almost never want to do a statistical test on the intercept. The intercept by itself, it's not such a useful parameter for statistical inference. For instance, for the palm width versus height data set, the intercept was 87, I think, saying that people with hand size 0 are 87 centimeters tall. there's not a lot of information there that we want to exploit statistically to make a decision, because it's not something that is of immediate physical value. So we're mostly interested in the slope, and we have the point estimate 0.11 and the standard error 0.234. And this then allows us to construct a confidence interval and to run a hypothesis test. So let's maybe look at the confidence interval first. So if we want to build a 95% confidence interval, then we will need a t-distribution with 14 degrees of freedom, because remember we had 16 observations. So 16 minus 2 gives us 14 for a t-distribution. And we also need a quantile that corresponds to the 95% confidence interval. So that's the 0.975 quantile. And if you ask R for that value, or you look in your table, then you'll get that that quantile is 2.14. And therefore we can derive our confidence interval for beta. So we have our point estimate, 0.16 here and here. We have our quantile, our t-value, t14 here and here. And then we also have the standard error here and here. So minus and plus here. And if you calculate that, then you get a confidence interval of 0.066 up to 0.166. So with 95% confidence, we know that the true population parameter is inside this interval. We don't have to calculate this by hand. If we're in R, we can use the confint command, and then that will spit out by default a 95% confidence interval. So you have the same values here and here. And of course, if you want a different confidence interval, there's an optional parameter that you can specify, say 90% confidence interval, 99%, and so on. So now with that, I want to return to something that we saw earlier in the plots, which is that for our data set, at least, when we looked at the diagnostic plots, we said, there are some things here that are not entirely correct. The QQ plot doesn't look like a straight line. There's maybe some trend in the residual plot here and here and here. So, okay, I can see there's a linear fit there, but I'm not entirely happy with it. So let's talk a little bit about how we can improve our model if we see that maybe a linear fit or a linear line isn't the greatest thing. So there's a couple of things that we can do, and what you have to do is going to depend on your data. Unfortunately, this is no one size fits all. So the first thing that we can do is something that you already did in the project and with hypothesis testing. If either homoscedasticity or the normality assumption fails, then or is not very well verified, then what we can do is we can try to transform our variables. And now we are dealing with two variables, the dependent variable and the independent variable, or the outcome and the predictor. And of course, we can transform either or both. So let's see a little bit what the effect is of doing that. So first, we can think about a transformation of the dependent variable. So remember, this is the outcome. And that is something that you can do if the normality assumption and the homoscedasticity assumption are not met. So in order to see why that is the case, think back about the plots that I had earlier, where we had a lot of right skew in our outcomes. So I drew a box plot before the break, and we had boxes that look like this. So for low values of X, they were relatively normal, but then for higher values of X, they had more and more skew, so something like this. So what we can do in that case is we can transform Y. If you have right skew, for instance, one of the things that you can do is you can do a logarithmic transformation. You can take the logarithm of the outcomes and use that to turn your observations back into something that is approximately normal. Will this always work? I don't know. It depends on your data. It is something that you can try. You can observe the results. You can look at the QQ plot and see if it makes an improvement. One thing that I want to say, which also came up during the project, is if you have positive data, so positive outcomes, for instance, counts or volumes like in the project and so on, so positive numbers, it's almost always going to be a good idea to try a logarithmic transformation. So keep that in mind. Not doing the logarithmic transformation is probably going to be painful and will need justifying. It's almost always a good idea. It's not the only transformation you can do. You can also take the square roots, square, and so on. But you have to apply them with a goal towards getting something where the normality assumption holds. And then on the other hand, we can also transform the independent variables, so the predictor or the X value. And that is not going to change the distribution of the Y for given X. And you can see that because all you're doing is you're shifting the X's around if you transform it. But given X, you don't change Y. And this is sometimes a good thing to do. It will not help you, of course, with the normality or the homoscedasticity, but it can help you with the linearity assumption if the normality is already taken care of. So let's say you have a data set that looks like this. So you have data points that look like so. So I try to give it, I try to make the noise look normal. And let's say you see a sort of a square root kind of dependence in there. If you then apply a square root transformation to X, then you may end up with something that looks more or less linear, like so. And in doing so, you will not have changed your distribution of Y given X. Again, this is something where there's no fixed prescription. You have to try out the transformation, make scatter plot, look at the diagnostics, see if the fit is better or not. So I already mentioned this in passing. A particular example of where homoscedasticity and normality will fail is if you have positive outcomes, or if you have outcomes that can only take values in an interval. Like, remember, normal distribution has support over the entire real line. So if you have only an interval of possible values, that's already a violation of your normality assumption. So if you see that that's a problem, then try transforming it, and in particular, try a logarithmic transformation. There's other, like these variance stabilizing transformations, but I will not cover that here. So what we can do for our data set at hand is we can try to transform the outcome. So for our data set at hand, the outcome Y was the coarse woody debris basal area. That is an example of a variable that's always positive. It's an area. So let's try to make it, to transform it in a bit to make the homoscedasticity look better. So what we can do in R is we can fit a new model, model 2. And now what we ask R is to consider not CWD, the beta, the variable, but the logarithm of that. And then one technical detail to be aware of when you do this yourself, you have to surround that expression by I, capital I. And this is an R command that stands for isolate. So this tells R, don't just apply the mathematical transformation, use the logarithm as part of your formula. So it's a technicality, but it has to be there. So if we do that and we look at our model, then what we're going to see is obviously the coefficients are going to change drastically, because now we're not longer looking at the variable, but we're looking at the logarithmically transformed outcome. So we get new estimates with new standard errors as a matter of fact. And if we look at the residual plots, now if we look at the normal, at the QQ plot of the residuals, then what we see here is we have a much better fit or a much better agreement with the straight line. So remember, before it was below and then above, but now we are almost completely on the line. However, if you look at the rest of the diagnostic plots, now we've sort of shot ourselves in the foot a little bit, because we've made the other diagnostics a bit worse. So if you look at the linearity here, now we want to see no pattern in the residuals, but now what we see is a clear increase followed by a decrease. So the linearity is not good. And likewise, for the square root of the standardized residuals, the scale location plot here on the lower left, there too, we want to see no pattern at all. But here we also see that there's a clear pattern where it decreases and then increases. So we've gained something, but we've lost another thing. So let's see what we can do about that in response. So let's focus on our linearity assumption. And what we can do is we can again try to apply different transformations. So we can, excuse me, we can try transforming either the outcome or the predictor. We've already played with that, so there's probably limited maneuvering space left in here. But what we can also do is we can fit a higher order model to the data. And in order to understand where that comes from, we can go back and we can look at our residuals at the top left plot here. And what we see is that there's a clear pattern here in our residuals where as the fitted values increase, we see first an increase in the residuals and then a decrease again. And that might prompt us to say like, okay, hey, if I look at that from very far, that looks like a parabola, an upside down parabola. So I have some pattern in my residuals that's not supposed to be there, and let's try to exploit it. So we might observe that, hey, there's some pattern in my residuals that looks like something quadratic, like we had up and then down again. So our residuals look like, if we, as a function of x, as a quadratic function. Then what that tells us about our outcomes here on the bottom of the slide is, if we add residuals with that pattern, then what we basically end up doing is we end up shifting our alpha, our intercept by a little bit. That's fine, we can live with that. We change our beta, that's fine, we can also live with that. But what we also end up doing is we see that we get a new term in our model that is proportional to the square of the observations. And so what the data is in fact telling us is, it's saying, well, I can't be fitted by a straight line perfectly well. I have a slight quadratic tendency, and I encourage you to model that tendency to get a better fit. And so let's take that at face value and see how far we can get with that. So what we can do now is we can generalize our model to go beyond a straight line model. We can say, well, the function that describes our data on average, in the beginning of the class, we call this f of x. Let's say that's no longer a linear function in x, a alpha plus beta x. Let's add a quadratic term to that, gamma plus x squared. And now that's a different model that we have to fit in a different way, but the approach stays the same. In order to fit this model, what we're going to do is we're going to look at the residuals, but now we have to keep in mind that our residuals will also have a quadratic term when we do the fitting. And how do we get, so we also get a new parameter, that gamma, and how do we get the values of the parameters? Well, now our objective function, the thing that we want to minimize, is a function of 3 parameters. And we will also have 3 conditions to satisfy: partial derivative with respect to alpha, with respect to beta, and with respect to gamma equal to 0. So then that will give you, if you calculate that, that gives you 3 conditions for 3 parameters. So in this way, you can find what alpha, beta, and gamma are. So we don't really cover matrix calculus in this course, but in fact, this model is as easy to solve as a straight line model. It's just one more parameter. And if you write this out in matrix form, you can see that really nicely, but we will not do that. So let's see how things look like in R. So if we want to take into account now this second term, this quadratic term, then we have to tell R about it. So what we do is, in our formula, we have the logarithm of the basal area that stays, is a function of the density of the trees that stays, plus the density of the trees squared. And that's because of that quadratic term that we want to add. And again, keep in mind that you have to surround that by an I for isolate, just so that R takes that square and puts it in the right place in the formula. Okay, so let's do that, and let's have a look at the outcome from R. So now we have 3 parameters, and we also get 3 point estimates from R back here. So 1 intercept, and then the coefficient. So this is alpha hat, the coefficient of the tree density, that's beta hat, and also gamma hat, the coefficient of the square term. We get the standard errors and so on. That is perfectly fine. And let me maybe devote just a few minutes to one thing that I've swept a bit under the carpet for now. Let's have a look at these p-values right here. So these are p-values. And what do these p-values represent? Well, they come from a hypothesis test, as p-values do. And the hypothesis test that R runs under the hood is, it runs a test where the null hypothesis is the population parameter is 0 versus the alternative, the population parameter is not 0. So for instance, if we take the last value here, let's take 0.00935. Here, the null hypothesis is that the population gamma is 0 versus the alternative is gamma is different from 0. And how does it find the p-values? Well, it again uses the fact that these parameters have a known distribution. I know what the standard error is, so I can plug everything into my one sample t-test formulas and obtain the p-value. You can perfectly well calculate it by hand with a calculator and you'll get the exact same p-value. Why do we care about this hypothesis test? Well, what does the null hypothesis tell us? Well, the null hypothesis says, well, gamma is equal to, oh, sorry, there should not be a hat here. Thank you for noting that, Chung-Hyun. So let me correct my mistake. With a hypothesis test, we always talk about the population parameters, not about the thing that we got from the sample, population parameters. So what does the null hypothesis tell us here? Null hypothesis says gamma is equal to 0. Gamma is equal to 0, if we turn that into words that are appropriate for the problem, means the gamma x squared term in my model does not matter. So does not matter. And what does the alternative hypothesis mean? Well, gamma different from 0 means the opposite, means that the term does matter. So what does the hypothesis test then allow you to do? Well, at a glance, it tells you which terms in your model are significant and which ones are not. So we could add more and more terms to our model. We could add a cubic term with the power 3 or power 4, or we could add anything else. And then we could ask, well, given the data, do you think that this term is significant in the model or not? And the p-value, the hypothesis test, is going to give us the answer. And here we see we have very small p-values. They're smaller than 0.01. So all of the terms are significant. All of the terms need to be included in our model to have a good fit. And by the way, note the convention with the stars. So double star here means that p-value is less than 0.01. Single star means less than 5%, and so on, as you see in the table down below. So at a glance, you can see which coefficients are significant and which ones are not, and then you can decide maybe to remove a term or not. So now, if we look at our plot, then what we have for our excuse me, what we have for our diagnostic plots is by adding this new quadratic term to our model, we see that the QQ plot for the residuals stays more or less okay. Everything is follows the straight line. Remember, with the QQ plot, it's possible that the first and the last points are off the line. That is definitely possible, but you want to see the bulk on the line. If we look at the residuals plot on the top left, we see now that, yeah, the residuals have much less of a pattern than they had before. So before it was really pronounced. Now we have something that is much more linear. And the scale location plot, the one that has the square root of the standardized residuals, here you can still see some pattern in the data. So you could try to add higher order terms or other terms to the model to try and improve that. But on the whole, this is maybe also something to be reasonably happy with, given the fact that you have only limited amount of data. And by the way, the last plot, the residuals versus leverage, we put that one aside. We will see that one in one lecture from now. And so if you wanted to continue with this model, if you said like, I'm not entirely happy with the scale location plot. That looks like a bit too variable to me. I think that there's probably a better model lurking out there that I can find. Well, nothing is stopping you from making a more involved model. What you can do is you can keep adding higher order terms to the model. So you can add, for instance, x to the power 3, x to the power 4, and so on. But every time that you add a new term, what you have to do is you have to fit the model to it with R and look at whether the inclusion of that term is significant. And if it turns out that R says that it is significant, then great, add it to your model. If it's not significant, then you do not add it to the model. And then you basically stop there. So in this case, if we were to add a third order term, so if we add x cubed, so now we have, we would have a model of the form y, or sorry, log y depends on x plus x squared plus x cubed. If I write it in pseudo formula language, if we add a third order term, x cubed, then we would find that the p-value is 0.26. So not significant enough to include. And you'll see when one of the next lessons, when we do model building, this is an example of hierarchically model building a model. So you start with a simple model and you add terms to get a better and better model until the data basically says, no, stop. The higher order terms are not going to be significant anymore. You're just fitting to the noise. One side note, when you add terms to the model, you should keep the lower order terms as long as the higher order terms are in the model. So let's say we add x cubed and we refit the model. Let's say, and so what's going to happen is when you refit the model, all of the data in your table is going to change. So all of the p-values, and it might be that one of the lower order terms becomes non-significant. So if we add x cubed and x becomes not significant, let's say, for example, p is 0.10, then even though it's not a significant term in the model anymore, you have to keep in x as long as you keep x cubed in or x squared. But that's a bit of an academic thing here, because as I mentioned, including x cubed is not going to give you anything. It's not going to be significant. Okay, so given that x cubed is not a significant term anymore, that gives us our final model. So in this case, we have something that has a linear term, so an intercept, a slope, and then a quadratic term. And we have that on average, the logarithm of the basal area, so ln of y, given the tree density, is given by this quadratic function that you have on the right-hand side as a function of the tree density. And we have to keep in mind that we're talking about the logarithm of the basal area. And that's good as long as we're doing mathematical modeling. But when we want to draw physical conclusions about our model, we need to turn it back into an area. So we need to undo the logarithm. So we need to take the exponential of what is given on the right-hand side. So that's how we get the following expression. So that is the exponential of the right-hand side. And then interpretation-wise, you also have to be a little bit careful with how you interpret what that expression in blue says. So here, originally, we had the expected value. So we know what that means. So the average of ln of y given x, but it's the standard average, the arithmetic average. But if we take the exponential of that, then we turn the arithmetic average into a geometric average, a geometric mean. So that's why we have that the geometric mean of the basal area for a given tree density is equal to that exponential expression. So there's a follow-up question about the model building. So when I'm going back to just one slide here, what you have to do is when you build a model, you can do two things. You can say, I have physical reason to believe that this is a linear model. And then what you do is you just fit the line. You don't add any higher order terms. And oftentimes having this kind of physical intuition is going to be useful because, as you can imagine, there are many terms that you can add to your model to try and improve it. X squared, x cubed, x to the fourth, sine of x, logarithm, any kind of transformation of x. So either you say, okay, I have one model that I want to fit, in which case you go ahead and fit it. Or you say, okay, I have a number of terms that I want to add to the model and I want to see how far I can get with that. And then if you do that, let's say for this model, let's say we want to add a quadratic term and a cubic term, x squared and x cubed. Then what the procedure tells you to do is you start with a linear model, you look at the fit, and chances are you're going to get a significant result. If it's already not significant with a linear term with an x, then you have to go back and sort of look at your research hypothesis again, because x and y are probably not related at that point. But assume that it is, then you have a nice linear fit. You have a slope. Slope is statistically different from 0. Then you add the next term, the x squared term. You refit the model, you look at the output from R, and you look at significance. And let's say the square, as it is here, is significant. Then, okay, you accept your model. You say, this is a better model than the purely linear one I had before. And then you move on to the next term, x cubed, and you again do the fit. And now let's say you observe that x cubed is not a statistically significant term. Then you do not add that to the model and you stop the fitting right there. You don't go to x4, x5 just to try and get something. You stop right there. You get a non-significant result, you stop. So you basically implicitly you rank the terms that you want to add in order of importance. And as soon as you find one that's not significant, then you don't try the others. You don't keep going x4, x5, x6 until you find something that would be fishing. But you stop right there and then you say, yep, my model is a quadratic model. And chances are that if you look at the diagnostics, that it's never going to look perfect. It's never going to be perfectly straight lines. There's always deviations from normality, but you have to accept that model fit is only as good as the data that goes in it. And yeah, there might be some hidden biases in your data, some sampling bias, but yeah, that's not something that you can. If you've done everything that you can to correct it, then whatever is left is unaccountable for, and then in your paper, you have to say like, okay, we obtained this fit, but you have to be a bit careful because look at the diagnostics. So, okay, I hope that was a bit meandering, but I hope that made sense in terms of this model fitting procedure. And we will do this again in the next lecture as well, when we talk about doing multiple linear regression. So coming back to our final model, now we can again use it for prediction. And we can, for instance, ask, well, what is the expected CWD basal area for 500 trees per kilometer? So X equal to 500. And if we plug that in, now we find a density of 0.086 square meters. And this is nice because now we get a positive value. Previously, we had a negative value, so negative is definitely unphysical. So we don't know how accurate this value is a priori, but at least it's positive, at least it's not totally unphysical. So now the last thing that we can do is, and I will just show you the formulas and then the plot. We will almost never have to use this explicitly by hand, but we need to be able to interpret it. What we can ask now is that estimate of 0.086 square meters. How precise is that? How confident can I be about this? What is the standard error? And in order to do that, we can take recourse to a couple of expressions for the standard error of the outcome in our predictions. And in particular, let's have a look at the standard error here of of our outcome, which we've written as y hat h for an input for a value of the predictor xh. Then what we have is that the uncertainty or the standard error on that mean outcome is given by the square root of the mean squared error again. So that's not too surprising. Remember, the mean squared error is basically some aggregate measure of the lengths of your residuals. So big residuals means you're going to have a lot of uncertainty in your model. So you expect the mean squared error to be there. And then times two other terms, or times a sum of two other terms. So we first of all have 1 over the number of observations. So if I have more observations, 1 over n gets smaller. So that also decreases the standard error. Conversely, if I have fewer observations, 1 over n will become larger, and I will also increase my standard error. And that makes sense because I know if I have more observations, I can be more confident about my outcome. If I ask 26 students about their heights versus if I ask 2,600 students about their heights, in the latter case, I can be more confident. And then the other term here is the difference of the predictor xh minus the mean of x divided by the sum of all of those deviations. So the difference between the observation xi and the mean x bar. So keep in mind x bar here, okay, here too is the mean of x. And what does that tell us? That's maybe a bit, it also makes sense, but maybe a bit harder to figure out. Well, when is this term that I shaded in green, when is that term small? It is small when the denominator, when the numerator is small. So when xh is close to the mean. So when xh is very close to the mean, the green term is going to be small, and therefore the standard error is also going to shrink. And conversely, if I'm very far away from the mean, xh minus x bar is going to become large, and the standard deviation is going to spread out. And what does that tell you about the linear regression? Well, it basically tells you that, and let me maybe make a small diagram of that. If I have my data points here, here, and here, and I have my line here, and let's say my mean x value is here, then I can be very confident for predictions that are close to the mean, but I can't be confident for predictions that are very far from the mean. So my prediction interval, if I exaggerate it a bit, is going to look like this, where the further that I'm away from from x bar, the more uncertainty I have in my predictions. And that makes sense, right? If I don't know if you remember how the height data from you, the students, looked like, but I had a lot of observations for palm width 7.5. So if you ask me for a prediction of palm width 7 or 8, close to 7.5, then I can probably be very confident. It's probably not going to be so different from what it was for 7.5. But if you ask me for a prediction that's very far away from 7.5, let's say 5 centimeters, a children's hand, or 12 centimeters, a giant hand, then I'm going to have much, much more uncertainty in those predictions because I'm much further away from the mean. So I have 3 things that contribute to my standard error. I have my residuals. So how good is the fit? I have my number of observations, and I have my distance to the mean or to the center. Okay, so that's the intuition behind the formula. We can also calculate it exactly, and we can use that again to build up a confidence interval for the mean outcome. So again, we're going to have a t-distribution for our predictions, and here what what we end up getting is that we have the mean outcome minus the expected value normalized by the standard error that we just derived is distributed along a t-distribution with n minus p variables, where p is the number of parameters in the number of parameters in the unknown model, in the model. So for a linear fit, we have that p is equal to 2. For a quadratic fit, we have p is equal to 3, and so on. So here we had alpha and beta. Quadratic, we had alpha, beta, and gamma, and so on. We will almost never have to calculate this by hand, although it's a good exercise to do that and to see that the outputs from R match with what you think it is. What we can do is we can ask R to calculate these confidence intervals for us. And in order to do that, we have to use a new command, the predict command here. So how does that work? Well, we take our model 3, the one with all the terms, and then we give it as the first argument to the predict function. And we also give it new data to predict on. And here you have to be a bit careful with how you supply the new data. This is something that I think R, not entirely happy with how R did it. There's probably a good reason for it, but it's a bit clunky for simple models like the one that we have. So you have to give your new data as a data frame. So here, what we want to do is we want to predict the basal area for densities from 800 meters to 2200 meters. That's what the 800 colon 2200 means. And we have to wrap that in a data frame call before we feed it to new data. If you forget that, you'll see it won't work. And we also have to ask for a confidence interval in the outcomes. And we do that by supplying interval equals string confidence. And what we will get out is a table of values. And we don't have the actual data here because they are pretty meaningless, but we have a plot on the next and last slide. And the predict is basically going to give us three things. Well, fit here is going to be the actual prediction. And then lower and upper are the bounds of the confidence interval. And by default, you get a 95% confidence interval. If you want a different interval, then you can add it as an extra parameter here. And then you have to keep in mind that the data that you get back from the predict call are logarithms of basal areas. So if you want to know something about the basal area itself, you have to undo the logarithm by taking an exponential. And that is easy to do. You just take each column of the result of the predict call and you feed it to the exponential call, to the exponential function. And so what we will get in this way is a table of data, and I can just add one more thing. So here the rows in this table with three columns is there's going to be one row for the prediction for 800, 801, 802, and so on. So then if we take the exponential, we're also going to get a vector of basal area for 800, basal area for 801, 802, and so on, all the way up to 2200. So we don't want to look at that data, or we don't want to look at that table. We want to look at the data. We can plot it in R. And here we have a couple of things. So choose another color here. The straight black line is the actual fit, what we think the mean outcome is going to be. And then the dashed lines here are the upper bound of the confidence interval and the lower bound. And again, you can see that the uncertainty increases by a lot as you go to the right of the plot. So the confidence interval blows up. And why is that? Well, again, we have, relatively speaking, a lot of data before 1400. So if I look at if I try to guess where the the X bar value is, probably X bar is going to be somewhere here. I haven't calculated it, but this seems reasonable. So for the predictions that are close to X bar, I can be relatively confident, as expressed by the quite narrow confidence interval. But the further away I get from X bar, the less and less confident I get, the wider my confidence interval becomes. And so that's the last thing that I wanted to say about this linear regression with one predictor. But in a nutshell, that basically covers everything that there is to know. So to sum it up and to finish it off, so what we've done today is, like, we've looked at how we can fit a straight line to the data, what there is to look at, like what diagnostics we have, what it is we can do with linear regression, so association and prediction, how we can improve a model, and then finally what we've done now, how we can interpret the results. And keep in mind, as with everything that we do in statistics, we're never happy with just a single number. We don't want an estimate without a measure of uncertainty. We always want to be able to say, this is my number and this is how confident I am about it. So I know it's been a lot of material and going slightly over time here. I will stop now and we will continue this story on Thursday. If there are any questions, please let me know. And then on Thursday, we will continue with our story. So thank you for your attention up until this point. I wish you a good rest of your day and I will see you on Thursday. Thank you.